Good morning, everybody. So we're starting a new section today. You can find this on page 424 in your book, going to page 425. And we're going to be dealing with the question of why is it that some things are able to sink or float? You think about the fact that, we have enormous steel ships which weigh, thousands and thousands of tons that are able to float on top of the water with no problem. Okay, so we're going to be taking a look at what principles are at work that are allowing objects to either sink or float. And the two things we're going to be looking at, two big ideas, we're going to be looking at both density and then another idea known as Archimedes' principle. All right, so let's take a look at density first. So we're just going to do a very simple experiment here involving some Coke cans. So I've got three different types of soda here. I've got some Diet Pepsi, some Sprite, and some Mountain Dew. Okay, now this was a fun game that we used to play when I was a kid in our swimming pool. You could actually go like diving for soda cans, and some types of soda cans, when you throw them in, would sink right down to the bottom of the pool. Others would float. We're going to take a look at what kind of soda cans are going to sink and which ones are going to float. Now, these are all unopened, so they're all full of soda. So we're going to do these one by one. I'm going to kind of stick them off to the side because there's like this little hollowed out region in the soda can. And sometimes the little air bubbles get trapped in there. It can actually like change the buoyancy of the can. So we're going to put it on its side. Okay, we're going to take a look. So we've got first our can of Mountain Dew. And I'm going to let go. All right, and we see that it sinks. So next we're going to go to the Sprite. And we're going to let it go. And we got another sinker. Okay, so we're going to go on to the Diet Pepsi now. Put it in, let it go. And look at that. It looks like my Pepsi or Diet Pepsi floats. Okay, so we're going to look at it. Why is it that some of these cans of soda are going to sink to the bottom of the water? Others are going to float. Okay. What I have here, I've got some scales set up. I'm going to wipe down our Mountain Dew here before I put it on the scale. All right, we're going to get the mass of my soda can. All right, so it looks like the mass of my Mountain Dew is 382 grams. All right, so now we're going to take a look at the difference between that and my Pepsi can, or the Diet Pepsi. Okay, turn that on. Put it on the scale. Okay, and it looks like, so my Diet Pepsi is only about 368 grams. All right, so even though they're exactly the same size can, one has a higher mass than the other. So the Mountain Dew is going to weigh more than the Pepsi. So we might think, okay, well that makes sense. Heavier objects are going to sink while lighter objects are going to float. Well, that's not always the case. So for example, right, got just a regular old penny right here. Right, now that penny is going to weigh a whole lot less than either of these two cans. All right, it's weighing less than my Diet Pepsi, yet when I put it in, we see that it sinks right down to the bottom of my fish tank there. All right, so there's more going on here than just lighter objects are going to float while heavier objects are going to sink. Because we got to remember, gigantic ships that weigh thousands and thousands of tons, they're made of steel, they're able to float no problem. So we know that very heavy objects can float, while very light objects like this penny are capable of sinking. So there's more than just whether an object is heavy or light that determines whether it's going to sink or float. So to understand what's going on here, we're going to go to the board. So in order to understand why it is one can of soda is going to float while the other one sinks, we have to look at more than just their mass alone. We're going to look at their density. Now, this is a little bit of review from way back in chapter 1 earlier this year when we talked about how to find density. So we're going back around understanding that in order to calculate density, you need to know the mass of the object and its volume. Okay, so density is going to equal mass divided by volume. So it's a ratio. In order to understand why something is going to sink or float, we're going to be comparing its density to the density of water. Now, if you guys look on page 425 in your books, you can see that there's this density column where they basically set up different types of liquids that have different densities. And different objects will sink or float depending on the substance that they're floating in. When we're talking about water, if you look on that diagram and find water, it lists its density as 1 gram per centimeter. In order for something to sink or float, it's going to be determined by whether or not the density of that object is more dense or less dense than the substance it's floating in. So in other words, the thing that's going to determine whether or not my can of soda is going to float or sink has to do with whether or not it's more dense than the water or less dense than the water. So let's take a look here. Okay, when I got the measurements for my can of Mountain Dew, we found that its mass, in this case, is 381 grams. Whereas the Diet Pepsi, its mass was 368 grams. Okay? Now I went through and I found the volume of both of these cans by putting them in some water, watching that water level rise. Remember, we call that displacement. That's something we're going to talk about a little bit later on when we get to Archimedes' principle. And then by taking that number, the new water level, subtracting it from the old water level, I was able to find the volume of both these cans. Now the thing to remember is both these cans have exactly the same volume. They're the same size. They take up the same amount of space. Okay? So in this case, both my cans have a volume of 375 milliliters. In other words, that's how much water the can of Mountain Dew displaced and how much water was displaced by the Diet Pepsi. So it's both exactly the same. In this case, they're the same size, they take up the same amount of space, they got the same volume. The only difference between them is their density, okay? So remember we said that density is determined by dividing the mass by the volume. So see if you can do this on your own. Take the mass, divide by the volume of both these cans of soda, and see if you can determine what the density is. So in the end, when you take the Mountain Dew can and you take its mass of 381 grams, divide by its volume of 375 grams, you come up with a density of 1.02. And remember, when we're talking about the units of density, in this case, because we're measuring mass in grams and we're measuring volume in milliliters, my density is going to be in grams per milliliter. Okay, so the density of my Mountain Dew can is 1.02 grams per milliliter. Okay, remember we said that the density of water is going to be 1 gram per milliliter. All right. Since the can of Mountain Dew has a slightly higher density than the water it's floating in, well, it's not going to float at all, and it will sink right down to the bottom. All right. So let's see if we can get the density of the Diet Pepsi. So its mass is, as we said, 368 grams. We're going to divide that by 375 milliliters, and that gives us a density, if I round here, of about 0.98 grams per milliliter. So when we compare the density of the Diet Pepsi to the density of water, we can see that Diet Pepsi is less dense than water, and therefore it's going to float. So this is really what's going on. When we determine whether an object is going to sink or float, you are going to compare its density to whatever density of the substance it is that it's floating in. In this case, pure water has a density of 1. If an object is going to float in water, it has to be less dense than the water. If it's going to sink, it means it's more dense than the water. Okay? Now, let's say if you were to change the substance up, like instead of trying to float something in water, let's say in this case, you wanted to float something in mercury. Well, in the PowerPoint presentation, if you looked it up, it is possible to get a iron ball, a solid iron ball to float if you're floating that object in mercury. All right, and the reason because you look down on page 325, you can see it lists mercury as having a density of 13.6 grams per milliliter. That's incredibly dense. That's 13 times more dense than water. And so most objects are going to have no problem floating in a vat of mercury because mercury has much more density. So whether something sinks or floats has to do with what's called the relative density. You're comparing the density of the object to the density of the substance it's floating in. And this also applies to when we're thinking about, say, why objects might float in the air. If you take a balloon and fill it up with air and let go of it, it's not going to float because the density of the balloon is greater than the density of the air that it's floating around in. But if you fill up that balloon with helium, that balloon now has a lower density than the air that it's floating around in, and so it's going to be buoyed up by the air. So again, whether an object sinks or floats in a fluid, and this could be any kind of fluid, this could be talking about a liquid or a gas, it's all going to depend on its density versus the density of the substance that it's surrounded by. So now we're going to take a moment to talk about how it is that objects are able to change their density. And you can see on page 426 in your textbooks, one of the examples that they give us is of a submarine. Now, submarines are just simply boats that are capable of changing their density on purpose in order to sink or float. Now, regular old boats, you don't want to change your density. All right, if you change your density, that means you're sinking and you're not coming back up. But submarines have the ability to pump water in and out of these objects called bilge tanks. And those bilge tanks are what's going to allow the submarine to sink or float on purpose. Now, we have to understand here, in order to change the density, you're going to be changing one of these two things, okay? So in order to change density, you're either changing the mass of an object or the volume of an object. With submarines, when they pump in more water into those bilge tanks, they're increasing their mass. When you think of it, volume is just talking about the size of an object, like how much space it takes up. When submarines pump water into those bilge tanks, well, the submarine itself is not growing any larger, it's not shrinking at all. The size of the submarine remains the same, so it's still taking up the same amount of space as it was before. So in other words, as it's taking on seawater, its mass is increasing. And as the mass increases, the density is also going to increase. So in order for that submarine to be able to sink, it has to increase its density just enough to where it's going to be more dense than seawater. Now here's the thing. It wants to make sure it's balancing out the amount of extra mass it's taking on, because if it takes on too much mass, well, it's just going to sink all the way down to the bottom of the ocean. If that happens, the submarine's in trouble, because remember we said that there are crushing ocean pressures way down deep at the bottom of certain parts of the ocean. Submarines don't want to go down that low. So they have to make sure that they're just increasing the mass just enough to allow them to sink and remain at a certain level or a specific level. So this is a very complicated process of figuring out just how much seawater you need to pump into a submarine in order to increase its density to just the right amount where it's sinking at a constant level, but it's not going all the way down to the ocean floor. There's another thing I could do to change the density of an object. And instead of changing its mass by either adding or taking away mass, you can also change an object's volume. In other words, without adding any additional mass or taking away any mass, you're just increasing the size of that object. A very simple example I have here is just of a balloon, all right? So if I take this balloon and add some air to it, now, yeah, I am adding just a tiny little bit of extra mass, but really what I've done is I have increased the volume. So this balloon now takes up a whole lot more space than it did before. And when I increase the volume, mathematically, I've just increased the value of the denominator. That's always going to have the impact of decreasing your quotient, okay? So in other words, as volume increases, the density is going to decrease. So as I keep adding more and more air, the volume is getting bigger and bigger and bigger, and the density of my balloon is getting less and less and less, okay? But if I do the opposite, okay, I start decreasing the volume of my balloon as I allow its size to decrease and it's taking up less and less and less space. Well, that's also having the opposite effect of increasing the density, okay? So changing the shape of an object, its volume, how much space it takes up, is going to be one of the things that's going to determine the density of an object and whether it's going to sink or float. Let's go back to the fish tank to take a look at how shipbuilders use this principle. So now we're going to take a look at how it is that engineers use these principles of buoyancy to allow gigantic objects like giant steel ships and steel tankers to be able to float. And to do this, I'm just going to use some aluminum foil. You can try this out at home if you like, making yourselves a little engineering project. So what I have here is just some aluminum foil that I've taken and I've rolled it up into a ball. Okay. Now the density of solid aluminum is about 2.7 grams per milliliters. Okay, so that's almost 3 times as dense as water. So if water has a density of 1, this has a density of 2.7. This is way more dense. Okay, and we can prove that it's more dense by taking it, putting it in the water, and we can see it sinks. Okay, now what if I told you I could get aluminum to float? Now, it's very simple. All I have to do is change the volume of the aluminum. So remember we said that if you could somehow increase the volume of an object, its density will decrease. Well, here I've taken the same exact amount of aluminum. So both of these objects, both the aluminum that I've wadded up into a ball and this aluminum here, they have exactly the same mass. So I haven't changed the mass. All I've done is change the shape of the aluminum. And by doing so, I've changed its volume. Okay, so we're going to see what happens when I take the same exact amount of aluminum and put it in the water. Here we go. And look at that. It floats with no problem. So this is the principle at work that's going to allow giant steel ships to float. Even though steel, the substance itself, is way more dense than water, if you can construct an object out of steel that has increased the volume of that object, you have now made it less dense than the water, and it will float very easily.